Imagine pulling critical strategic minerals out of pitch-black ocean water 4 miles down, where the pressure would crush a submarine like a soda can. That is not science fiction anymore. It is happening right now in the Western Pacific, and it could break China's tight grip on high-tech manufacturing forever. Welcome back to Taranov's Geopolitics channel. In today's deep dive, we are uncovering Japan's quiet breakthrough 6,000 meters beneath the ocean floor. We will break down how ancient microscopic fish teeth trapped rare elements, how custom Japanese drilling ships pulled 50 tons of ore-bearing mud from the deep, and why Beijing's recent trade restrictions are forcing Tokyo to race against time. Stick around and watch till the very end, because the economic and geopolitical stakes at play here will shape the tech industry for the next half-century. On July 24, 2026, Japan's Cabinet Office and the Japan Agency for Marine Earth Science and Technology, known as JAMSTEC, dropped a landmark update. The announcement was understated and full of dense technical jargon, detailing a comprehensive chemical breakdown of seabed mud recovered earlier in the year. Yet, inside the context of Tokyo's long-running Minamitorishima rare earth program, this was a massive historical leap. Now, to be clear, Japan did not magically spot brand new rare earths in the Pacific overnight. Researchers have been studying this area since at least the early 2010s. What changed in 2026 is that Japan proved it could continuously pump ore-rich mud all the way up from nearly 6,000 meters below the waves, revealing an astonishing concentration of medium and heavy rare earth elements. So where exactly is this giant underwater gold mine sitting? The action centers around Marcus Island, also called Minamitorishima, a tiny coral atoll sitting isolated in the western Pacific between 1,900 and 2,000 kilometers southeast of Tokyo. The island itself is practically a speck on the map, but its true power is the massive exclusive economic zone wrapped around it. That zone grants Japan full sovereign rights over a gigantic chunk of the deep sea floor that would otherwise be open international waters. Look, the treasure isn't sitting under the dirt on the island. It's scattered across the pitch-black ocean floor way south of it. Back in 2012, the University of Tokyo did a survey showing a 2,500 square kilometer area that might hold anywhere from 6.8 to 16 million tons of rare earth oxides. Those numbers jump around depending on which study you read, because these are early geological guesses, not fully proven commercial mines. Right inside that zone, scientists found a sweet spot called the B1 area, 105 square kilometers, where just the top 10 meters of mud contain over 1 million tons of rare earth oxides. To visualize what this looks like, forget everything you know about traditional hard rock mines with visible veins of glittering ore. This is an eerie, vast, sediment-covered seabed sitting between 5,700 and 6,000 meters underwater. Down there, hydrostatic pressure reaches 600 atmospheres, water temperatures hover just above freezing, sunlight is non-existent, and biological activity moves at an absolute crawl. The material itself is a fine pelagic deep-sea sediment solidified over millions of years, made of fluorapatite, phillipsite, quartz, albite, illite, and montmorillonite. Crucially, the rare earths are not spread evenly across these minerals. One specific mineral hoards almost all the metal, and that is the secret key to this entire mystery. Taranov's analysis is built on examining how nature creates strategic leverage. And here the deposit comes from a million-year cocktail of ocean chemistry and biological waste. Rare earth elements float in seawater in tiny concentrations. When marine organisms die, their remains slowly sink, absorbing trace metals on the way down. Among that debris are microscopic fish teeth and bone fragments made of apatite, a calcium phosphate mineral that acts like an absolute magnet for rare earths. While phillipsite in the same mud holds only 60 to 170 parts per million of rare earths, biogenic apatite grains hold an incredible 9,000 to 32,000 parts per million. So the pipeline is simple. Seawater feeds marine life, bones and teeth concentrate the elements, apatite traps them, and millions of years of burial create a massive Re-rich seabed deposit. Now, why does this specific ocean spot matter so much to world powers? Because the geology heavily favors heavy rare earths, which are far rarer and way more expensive than light ones. Some of the top-grade mud hits 7,000 parts per million overall, but the apatite in those fish bones can top 20,000 parts per million, meaning over 2% of its total weight is pure rare earths. Hold tight, because in just a minute we're going to break down the incredible technology Japan built to haul this mud up 6 vertical kilometers. So stay right here. This brings us directly to the game-changing July 2026 lab results. JAMSTEC tested the mud pulled earlier in the year and confirmed that medium and heavy rare earths made up roughly 54% of the total rare earth content, with light rare earths making up the remaining 46%. Yttrium was the biggest winner, taking up 30% of the blend. Neodymium, the crucial ingredient for electric vehicle motor magnets, made up 18 to 20%, while heavy elements like gadolinium and dysprosium accounted for 5% each. To be clear, 54% doesn't mean the mud is half rare earths. It means that out of the rare earths present, over half are the valuable medium and heavy types. Japan has kept quiet on the total overall concentration percentage, stating that short test runs don't give enough data yet. So why did this precise spot in the Pacific get so insanely enriched? It comes down to extreme isolation. The deposit sits so far from any major continent that very little ordinary dirt, sand, or clay blows in to dilute the rare earth material. If this were near a major river mouth, the fish bones would be buried under billions of tons of mud. But in the deep ocean, sedimentation is painfully slow. Add millions of years of steady bone rain, shifting ocean currents, and zero continental pollution, and you get an ultra-concentrated layer of strategic high-grade mud sitting right on the seafloor. Okay, so here's the really cool part about processing this stuff. Because the rare earth bones are larger than the surrounding fine clay, Japanese researchers figured out they can use a basic hydrocyclone system to spin and separate the big grains right away. I mean, honestly, shipping hundreds of tons of useless ocean dirt back to land for chemical refining would just burn money fast. So doing this pre-filtering step completely changes the financial equation. They pump up the raw mud, spin out the seawater and fine waste, keep the heavy apatite grains, and send a super concentrated batch to mainland refineries. Taranov's analysis is vital for cutting through hype, and despite the great geochemistry, mining 6,000 meters down is a monumental engineering nightmare. Japan has to run a vertical pipe system nearly 6 kilometers long, the equivalent of stacking 16 Empire State Buildings on top of each other from the ocean floor to a surface ship. During the early 2026 test, the drilling vessel Chikyu deployed a closed circulation riser pipe made of 610-meter segments, reaching a depth of 5,700 meters. They successfully pumped up 50 tons of slurry in the world's first continuous deep-sea rare earth extraction, while JAMSTEC deployed underwater acoustic and environmental DNA sensors to monitor seabed disruption. If you're finding this fascinating, stick with us. We are about to look at the upcoming 2027 full-scale trial and China's sudden export bans. The next phase pushes the boundaries even further. In February 2027, Japan plans to launch a month-long trial aiming to scoop up 350 tons of mud every single day. The raw material will be dewatered right on Minamitorishima Island and shipped to the mainland to test large-scale smelting and refining. According to JAMSTEC project manager Kazushige Kikuchi, Japan will complete a full assessment by March 2028 to decide if domestic commercial production is realistic. There is another massive advantage hidden in this mud. It is remarkably clean. JAMSTEC confirmed that the samples pulled in 2026 contained no detectable radioactive or toxic elements. Traditional landmines usually contain uranium and thorium, which leave behind dangerous radioactive waste and drive up processing costs. Since Minamitorishima's metals are locked in organic fish bones rather than hard rock minerals, commercial refining could carry a significantly smaller environmental footprint, though full testing across the entire field is still required. Now, why is Japan sprinting to make this work right now? Because global rare earth supply chains have turned into a geopolitical battleground. China currently controls 70% of global mining and over 90% of rare earth refining. Japan relies on China for 63% of its rare earths, and that vulnerability exploded in April 2026 when Beijing restricted exports of heavy rare earths and magnets in response to United States tariffs. Japanese auto production sputtered as magnet imports plummeted, while political tensions between Tokyo and Beijing reached new highs. Prime Minister Sanae Takaichi has publicly championed the Minamitorishima initiative as a vital shield against foreign economic pressure. She highlighted these elements as non-negotiable for Japanese automakers and semiconductor foundries, promising full government backing for resilient domestic supply chains. However, several market analysts point out that deep-sea mining remains a long-term political gamble, noting that Tokyo will still depend on Chinese refineries for years, while engineering hurdles get worked out. Taranov's analysis is clear on the ultimate takeaway. This is a bold attempt to turn ancient ocean history into modern industrial security. Deep beneath Minamitorishima, millions of years of seawater chemistry, volcanic ash, and prehistoric fish remains have aligned to form a massive strategic reserve. Japan has proven it can reach 6 kilometers down and haul that wealth to the surface. The remaining question is whether Tokyo can scale this operation to hundreds of tons a day at a cost the global market can support. A question that will be answered when the 2027 trials conclude and the 2028 final verdict is delivered.
If you like this podcast, please like, subscribe, and share.